So I thought I'd do a slide on Taylor Polynomials for those who missed class on Thursday and for some who may not have understood it very well. And since the test is coming up, I thought this might be a good time to start practicing doing those online lectures anyway. So, Taylor Polynomial. From Tuesday, remember that we figured out that a function centered at 0 can be written in this form, where this stands for the nth derivative and we plug 0 in. If we can find the pattern for this, we can come up with a formula for the Taylor series for particular functions. So, first, let's remember the geometric series. Geometric series just means you start with something and each time you multiply by r. And if this r is less than 1, we know that the sum of the series is a over 1 minus r. So if we do the same thing, but we're looking at a polynomial, 1 plus x squared, this is a geometric series. We start with 1, the r that we multiply by at each step is an x. So as long as the absolute value of x is less than 1, this polynomial represents this function, 1 over 1 minus x. So that gives us our first formula, and we can start using the formulas to come up with more complicated Taylor series. Okay, let's look at e to the x. So this one we have to go through and look for a pattern. Well, if we need to figure out a pattern for the nth derivative with 0 plugged in. Okay, so f of x is e to the x, you plug 0 in, you get 1. You take the derivative of e to the x, you get e to the x. You plug 0 in, you get 1. If you take the third derivative, or second derivative, you're going to get e to the x. You plug in 0, you get 1. So all of these will be 1. F to the n was 0, all of them will be 1. So, oops, you can't see that. Let's see if I can pull that down a little bit. Yep. So the formula for e to the x would be the summation as n goes from 0 to infinity. I didn't bother putting a 1 there because it's a 1, but you have x to the n over n factorial. Can I make this bigger? No, I can't. Oh. Okay, so that's our formula for e to the x. Let's look at sine x. Now in class I broke you up into groups to do this, but I don't have groups here, and my cats aren't really good at math. So let's see what we do for sine x. So the first derivative of sine, nope, not yet. You have sine x, plug 0 in, you get 0. Derivative of sine is cosine. You plug 0 in, you get 1. Take the next derivative, you get negative sine. You plug 0 in, you get 0. Take the derivative of that, you get negative cosine. You plug 0 in, you get negative 1. Take the derivative of this, and you're back where you started, at sine x. You plug 0 in, you get 0. So this f sub f nth derivative with 0 plugged in will be 0, 1, 0, negative 1, 0, etc. So just kind of flip back and forth. So we need to figure out how to write this. So notice it's only the odd derivatives that survive. So I've got 1 over 1 factorial x to the 1. And they're going to alternate. So I have minus 1 over 3 factorial x cubed. Plus the next one is 5. 1 over 5 factorial x to the 5. So I need to get all the odd powers and make sure they alternate. So the formula we use is negative 1 to the n. That makes sure it alternates. But we only want the odd powers. And the standard way to write an odd number in mathematics is 2n plus 1. So if n equals 0, we get x to the 1 over 1 factorial times a positive 1. If n equals 1, we now have a negative, and x is raised to the third power over 3 factorial. Now we want to find cosine. Now in class we cranked it out and did all the possible, and did the same thing we just did for sine, but there's an easier way. The derivative of sine is cosine. So here's my sine function. I take the derivative of sine, I get cosine. I take the derivative over here. Well, this is just a power rule with a bunch of other crap sitting around. Cat, sorry. The n plus 1 comes out front. I subtract 1 from the power. I now have x to the n. N plus 1, 2n plus 1 times 2n over 2n plus 1 factorial. Those will cancel. I'll be left with just 2n on the bottom. So that is my formula for 2n. Cats are such assholes. Anyway, so I've got cosine of x. That's my formula for cosine. Now, next, let's do tan. Tan is sine over cosine. And that's my sine function, and that's my cosine function. So I can do long division. See, so we have cosine divided into sine, and let's see, we do long division. So 1 goes into x times, so that's my first thing in the quotient. X times all of this gives me x minus 1/2 x cubed plus 1 over 24 x to the 5th minus blah, blah, blah. Big old subtraction. The x's subtract. That's why we did it. Negative 1/6 minus the negative 1/2 gives me 1/3. I did all the other oogie fraction subtraction on Maple because yuck. So now I have the next one. 1 goes into 1/3 x cubed. 1/3 x cubed times. Multiply that through with the divider. Subtract. And you have, you have a remainder so far of 2/5 x to the 5th minus 4 over 315 x to the 7th plus a whole bunch of other shit over here. And we can keep going and we will get this. And this is a pain in the ass and we're not going to do it. I actually looked online to see what the formula for tan x is. And basically, every time I look, I get these first 3 terms and that's it. Or some weird notation. So just know that if we have to have tan x, we can look it up in a book. We don't need to put it on a test or a quiz or anything like that. What's next? Yeah, this is a smiley face. What's next? Okay, so we can do these things without going and looking for the pattern. Let's say I want to do e to the 3x. Now I already know the equation for e to the x. It's x, whatever's here, it's raised to the nth over n factorial. Well, over here I have 3x instead of x. So I will plug 3x into where this x is. So we'll have 3x to the n over n factorial. Now I simplify. This is algebra. 3x to the n is 3 to the n, x to the n over n factorial. That's my Taylor series for e to the 3x. Well, what if I have x times e to the 3x? Well, I already know what e to the 3x is. Oops. That's here. And I multiply by x. So when I run it through this big honkin' sum, I just have x to the n plus 1. Now, let's check this one out. We have 1 over 1 plus x. And we know the formula for 1 over 1 minus x. So it's this over here, which you can't see because this keeps blocking out. But I have 1 plus x. So what I really want for this formula is 1 over 1 minus crap. If I can write it that way, I can put the crap in for the x over here, and I'll have my formula. Well, 1 over 1 plus x is 1 over 1 minus negative x. So this is my crap. This gets placed here. I'm going to simplify. Negative x is the same thing as negative 1 times x. So I've got negative 1 to the n, x to the n. Did I say to the x? Oh, no. Okay. Now, here I have 1 over 2 plus x. I don't want that 2 there. I want it to be a 1. So what I'll do is I'll suck out the 2 from the bottom. Suck out a 2 here and from both. You get 1/2, you get 1 minus a negative x over 2. I went ahead and did that negative trick too. So this 1/2 is just a constant we're going to stick out front, and this is my 1 over 1 minus crap. Crap goes in for x. So you've got negative x over 2, all raised to the n, and that 1/2 is on the outside for now. So I can distribute the n, so I'll have negative 1 to the n, x to the n. On the bottom, I have 2 to the n, but I've got 1 more from the outside, which I will distribute through. So now I have 2 to the n plus 1. So that is my formula for 1 over 2 plus x. What about this one? 1 over 1 minus x quantity squared. I can't pull that trick because I have an x squared. Everything is squared. If I multiplied the sucker out, I'd have 1 minus 2x plus x squared, and oh, it would just be gross. I guess we could do a completing the square, but an easier way would be to notice that this is the derivative of this with a negative missing. So that's what we're going to do. This is negative the derivative of 1 over 1 minus x. And I know that 1 over 1 minus x is x to the n, as n goes from 0 to infinity. So now I take the derivative of that, have negative n times x to the n minus 1, because you bring the power down. I'm pointing with my finger, that doesn't do much good. You bring the power down out front and subtract 1 from the power. And I went one more step, because I said from n goes from 0 to infinity, but if n is multiplied through, that first term is just 0. There's no real sense in starting with 0, so we can write it as n goes from 1 to infinity. These are both correct, but that's kind of stupid. Let's do, ooh, that one went fast. Okay, so now I have 1 over 1 plus x squared. So I can think of this as 1 over 1 minus negative x squared. So I've got negative x squared to the n. So I've got negative 1 to the n, x to the 2n. Now, I'm going to integrate both sides, because I can do that too. If I integrate 1 over 1 plus x squared, we all know that that's arctan. So I have a big ol' hunk of integral sign over here, and I just need to integrate this. And this is just the power rule. We've got some shit over here, but then we have x to the 2n. You add 1, divide by what you get, plus c. In class, I kind of rolled over this, but I won't do this now. I'm going to fix it. So since arctan of 0 is 0, that means my c is 0. So that's why I kind of ignored it in class on Thursday. So building all that in, the formula for arctan is negative 1 to the n times x to the 2n plus 1 over 2n plus 1. So I think that's n, yeah. So what I want you to remember from this is we've got some basic formulas. Don't reinvent the wheel. If I ask you to do something with arctan, you have a formula for arctan. If I ask you something of, like, I think x squared over 1 plus 3x, you can massage that so it looks like one of our formulas. Don't try to do the first derivative, second derivative, third, and try to find a pattern, because it may be hard to see. So there's the Taylor series. If you've got questions, call me, beat me, whatever. You have all my information. So thanks.